Welcome back. So in the last section we started with the general solution to the time independent Schrodinger equation, and we applied the boundary conditions associated with a particle living in an infinite potential well extending from x is equal to 0 to x is equal to L. The first boundary condition set A is equal to 0, and the second boundary condition calculated the functional form of the wave number k, which is n pi over L. And I note that k actually depends on an integer n, and we're hinting at quantization here, but we'll come back to that later. Now, in order to know everything about the solution for our particle in our infinite potential well, we need to calculate the functional form of this constant b. Now, in order to do that, I'm going to invoke the normalization criterion. If you don't know about this, I refer you to my video where I discuss basis states. Essentially, it means that the probability of finding our particle anywhere in the well must be 100%, which mathematically means we're going to take an integral within the well and it's going to equate to 1. The mathematical definition of our normalization criterion is given at the top center of your screen, where we take an integral over all space of the product of our wave function and its complex conjugate, and that's equal to 1. Note that sine clearly is a real function, hence there is no reason to take the complex conjugate. Hence we're integrating over all space the square of the wave function and equating it to 1. But we know that in the region of x less than or equal to 0 and x greater than or equal to L, the wave function must be 0. And that basically allows us to simplify our integral. We don't need to integrate over all space, and simply just integrate x is equal to 0 to x is equal to L. If we plug in our wave function, we get this integral here. And notice we're integrating sine squared. Now, this can be a rather tricky integral to solve, and I have solved it in a previous video, and I'm simply going to draw on the results of that here, as opposed to solving it outright. If you're solving an integral with sine squared, now the argument of the sine squared doesn't matter, provided it is a function of x, and we're integrating along an even integral. In this case, negative to positive n pi. The result is going to be n pi. Similarly, if it's integrated from negative to positive L, the answer is going to be L. Now, our interval is half of that, hence it's going to be from 0 to L, and the answer, or the evaluated sine squared, is going to be L over 2. And we have our solution. We plug in L over 2 instead of our integral, and we equate and solve for b, and we get a square root of 2 over L. And we know that the wave function which describes a particle living in an infinite potential well extending from x is equal to 0 to x is equal to L is given as square root of 2 over L outside of sine n pi x over L. Note, of course, that we still have this integer n. This is known as the principal quantum number, and this means that our wave functions are distinct and separate. I'll talk more about that in a moment. So the question is, what does the wave function itself actually look like? In front of you, I've plotted the square of the wave function at n is equal to 1 and n is equal to 3. Now, the reason I've plotted its square is because that's what's measurable, and we're not really interested in why at the moment, but just take that for fact. So the red curve is n is equal to 1, and the green curve corresponds to n is equal to 3. Now what I'd like to talk about is the energy associated with each wave function and the wavelength, or put differently, the energy associated with the particle described by each of the particular wave functions in our infinite potential well. Now, when we solved the time-independent Schrodinger equation, we derived this particular expression for the energy in our system. And of course, it's a function of the wave number k. But we calculated the functional form of the wave number k, which we plug in, and get the functional form of our energy of a particle corresponding to any of our wave functions. We note, of course, that it is a function, or depends on, the principal quantum number n, which is an integer. And this basically means that all of the energy levels are distinct. which is completely different to classical mechanics, where we can have a continuous or continuum of energy levels. In quantum mechanics, the energy levels are quantized. Clearly so, we have to have a distinct wavelength corresponding to each wave function. We know that the wave number k is twice pi over lambda, which we equate with n pi over L, and we calculate the functional form of our wavelength, which is twice L over n. And that's really it. That's the solution to the time independent Schrodinger equation, which describes a particle living in an infinite potential well from x is equal to 0 to x is equal to L. And then in the next section I'm going to talk about the language associated with these wave functions, and a small bit about using them as basis for other wave functions.